This video is all about how to calculate the pipe size. Now, using the AGA method, which is the American Gas Association method, calculate the transmission factor, friction factor for a gas flow rate in an NPS of 20-inch pipeline with 0.375-inch wall thickness. The flow rate is 250 mm standard cubic feet per day. That is 250 million standard cubic feet per day. Gas gravity 0.6 and viscosity 0.000008 pounds per feet seconds. The absolute pipe roughness is 600 micro-inch. Assume a bend index of 60 degree, base pressure equal to 14.73 psia and base temperature equal to 60 degrees Fahrenheit. If the flow rate is doubled, what pipe size is needed to keep both inlet and outlet pressure the same as that at the original flow rate? So now let's begin. Now we need to calculate for the internal diameter of the pipe. Now the tire diameter, which is D. Now we are given the outer diameter. So the internal diameter, which is D, is equal to outer diameter minus 2 times the thickness. Because if you see, if you look at, there is a pipe now. Now this inside here is what we call internal diameter D. Now this small size here, which is the thickness T, see T appears 2 times. So while this length here from here to here is our outer diameter. So if you can see that the internal diameter will now be this outer diameter minus the thickness, the wall thickness minus the wall thickness will give you this. So you are minusing the wall thickness 2 times. That is why you have minus 2t to give you the outer diameter. So that is how we got this formula. Now you have the outer diameter to be 20 minus 2 times the wall thickness, which is 0.375 inches. So we have 20 minus, this will give us 0.75. So 20 minus 0.75 will give us 19.25 inches. Now we also need to calculate the base pressure. Now the base pressure, we are not going to use 60 degrees Fahrenheit. We're going to convert this to Rankine. So to convert to Rankine, we just need to add 460 to 60, which will give us 520 degree Rankine. Now let's write down some of the given values, or we can say the given data. Now we are given the outer diameter to be 20 inches. We are given the wall thickness to be 0.375 inches. We are also given the flow rate to be 250 times 10 raised to power 6 standard cubic feet per day. Now we are also given gas gravity to be 0.6. We are given the we're given the viscosity to be 0.000008 pounds per feet seconds. We are given the roughness, pipe roughness to be 600 micro inch, which is 600 times 10 raised to power minus 6 inch. Now we are also given the bent index to be 60 degree, and then we are given the base pressure to be 14.73 psi absolute as psi absolute. Now we are asked to calculate for the transmission factor and the friction factor. Now making use of the AGA, which is the American Gas Association. But first, before we do that, before we start making use of that, we need to calculate our Reynolds number. Now, our Reynolds number, the formula for Reynolds number is 0.00047778 times the base pressure divided by the base temperature times G times the flow rate divided by the viscosity divided by the internal diameter. So this is a formula to calculate our Reynolds number. So that is it. So now we are going to make use of this formula to calculate our Reynolds number. So to be calculating our Reynolds number, now let's say the Reynolds number will now be 0.00047778 times the base pressure, which is 14.73, times the gas gravity, which is 0.6, times the flow rate, which is 250 times 10 raised to power 6, divided by the base temperature, which is 520, divided by the viscosity, which is 0.000008, divided by the internal diameter, which is 19.25. So what's our Reynolds number? Let's calculate it. Now from here, our Reynolds number will now be what? Let me see. We have 0.00047778 times 14.73 times 0.6 times 250 exponential 6 divided by 520 divided by 0.00008 divided by 19.25. So we have let me write it down. I have 13,180, sorry, 13,183,055, okay, and 55, or I'll say and 56, 56. So what we have is, let me now write it. I have 13,183,000 and what, 56. So this is our Reynolds number. This is what we got. So now Having gotten this, we now have to calculate for our transmission factor and the friction factor. So now, if we, for us to start, we are asked to use the AGA method. What is the meaning of this acronym? Is what is it's called the American Gas Association. So the American Gas Association now had now set up a method. So now the method, what's the method is all about is first first we calculate using the full turbulence zone. Now, first using the full turbulence zone, we say F will now be, which is the transmission factor, it will now be 4 times log 3.7D divided by E base 10. So now, in this scenario, we are considering that the pipe is rough. We are considering pipe, rough pipe. We are considering rough pipe flow. Now, if we are considering rough pipe flow, that means we will be ignoring the Reynolds number. In this equation, we ignore the Reynolds number. So that is how this one comes about. The Reynolds number is being ignored. Now we are considering the rough. So now, if we calculate this, then we also calculate the second one, which now we now consider it to be a smooth pipe, where we now consider the partial turbulence zone, where we are looking at the Reynolds number. Now, which is the second formula. Now, this is all about the partially turbulence zone. Now, we are considering a smooth pipe. So, considering a smooth pipe, you have the F to be equal to 4 times the draft log Reynolds number divided by 1.4125 ft. Now, this is our transmission factor. Now, and this Ft is equal to 4, this is base 10, sorry, 4 log Reynolds number divided by Ft base 10 minus 0.6. So now where our Ft is the von Karman smooth pipe transmission factor, and the drag, so the drag factor is equal to the pipe drag factor. Now that depends on the bend index. This depends on the bend index, the BI of 5. Now, the way to use this formula is after we must have calculated the first one, which is a full turbulence zone, where we are considering rough pipe, considering it to be a rough pipe, then we calculate considering it to be a smooth pipe. Now, in this case, you're taking off the rough factor, the roughness, that is the E, the pipe roughness, you're taking it off, which is E, and you're only considering the Reynolds number effect. So what we're considering here is if the pipe is smooth. Now you now calculate this F here. So finally the F we're going to use, the transmission factor we're going to use is the smallest of these two. Let's say we have F1 to be a value, to have a particular value, and F2 to have a particular value. Then the F1 is for full turbulence zone, the full turbulence zone, then the F2 is for the partial turbulence zone. Now, if F1 is less than F2, so the answer will now, the transmission factor will now be F1. But if F2 is less than F1, so we now use this to be our transmission factor. So in essence, what I'm saying is that when we calculate using the first condition and the second condition, whichever is the smallest will be the transmission factor. That is what I'm saying in essence. Now, the bend index is the sum of all the angles and bends in the pipe segments divided by the length of the pipe section under consideration. Now, let's proceed. First, let's use the first condition where you have F to be equal to 4 log 3.7D divided by E base 10. So we have 4 times log 3.7 times 19.25, which is our D, divided by our E, which is 600 times 10 raised to the power minus 6. Now let's calculate the F factor. Let's now invoke our calculator to do this. So now we're going to make use of our calculator. Now we have 3.7 times 19.25 divided by 600 exponential minus 6 equal to this. Now log to base 10 times what? 4. So what's the final answer? Final answer 20.30. So 20.30 into 2 decimal place. So now we have calculated using the first condition. Now using the second condition, we needed to first calculate the von Kammer smooth pipe transmission factor, which is Ft equal to 4 log Reynolds number divided by ft base 10 minus 0.6. Now let's assume ft to be equal to this value 20.30. We make an assumption. So now our ft will now be calculated. Now we are going to calculate the ft using this assumed value on the right hand side. So we'll now have 4 times log the Reynolds number. So our Reynolds number is what? Is 13,183. Sorry, 13,183,000 and what? 56. So divide by the assumed Reynolds number. So short, the assumed Vancomycin smooth pipe transmission factor, which is 20.30 minus 0.6. So let's now invoke the calculator and make use of it to calculate this. So we have 13,183,056 divided by 20.3 equal to this. So now we now look at the log of that times 4. We'll have 23.25 minus 0.6. So we have 22.65. So what we have is 22.65. So since this value is far from this value, since there are great deviations, so now we need to recalculate, assuming the von Kammer smooth pipe transmission factor to be 22.65. So 22.65. So now we're going to now assume it to be that. So assume the smooth pipe transmission factor to be equal to 22.65. Now let's calculate for this. So now we have 4 log the real number, which is 13,183,056 183,056 divided by 22.65 minus 0.6. So what will this give us? Let's invoke our calculator and do that. So what will this give us? It will give us, this is base 10, sorry. Now let's check what this will give us. It will give us what? Now we have 13,183,000. This point there, sorry. 13,183,056 divided by 22.65. Now we have this. Now we say log to base 10 times what? 4 minus 0.6. So we have 22.46. So we have 22.46. So 22.46. Now let's assume there's still deviation from this value on this. So now assuming ft to be equal to 22.46. So now our ft will now be 4 log 13,183,000 and 56 divided by 22.46 base 10 minus 0.6. This will give us what? Let's look at it. So we have 13,183,056 divided by 22.46 and 46 equal to log base 10 times 4 minus 0.6. So we have 22.47. So we have 22.47. So now approximately based on trial and error, we're able to get our FT, which is our smooth pipe transmission factor, to be 22.46. So this is it. Now let's now make use of this to calculate our transmission factor. So the transmission factor will now be 4 times the draft factor log Reynolds number divided by 1.4125 ft base 10. Now what is our draft factor? Sorry, our drag factor, not draft, drag factor. Now for us to calculate our drag factor, we are given the bend index to be 60 degrees. Now assuming it is a bare steel, now let's look at this table. Now for a bare steel, bend index of 60 degrees, so we are making use of 0.96 as our drag factor. So our drag factor will now be 0.96. So drag factor is 0.96. That is what we're going to use. So a drag factor from that table is 0.96. That is what we got. Now we are going to apply this in this equation. So since F is equal to 4 times the drag factor log Reynolds number divided by 1.4125 ft base 10. So we now have 4 times the drag factor, which is 0.96 times log Reynolds number, which is 13,183,056 divided by 1.4125 times our smooth pipe transmission factor, which is 22.46 base 10. So let's make use of our calculator to calculate the transmission factor in the second condition and compare it to choosing the smallest of them all. So we have now 13,183,056 divided by 1.4125 divided by 22.46 also this log. So log this is what we get times 0.96 times 4 equal to 21.57. So we got 21. So what we got here is 21.5, not 5758, 21.58. So Since the second scenario is greater than the first scenario, so the answer, the transmission factor will be, what we choose is the smallest value, which is 20.30. So now we're going to use this to calculate our friction factor. Use our transmission factor to calculate our friction factor. So the relationship between friction factor is and transmission and the relationship between friction factor and transmission factor is transmission factor equal to 2 divided by the square root of the friction factor. Now, which then implies that now if we multiply both sides of the equation by the friction factor, or let's say we take the inverse of both sides. Now, the inverse of the right hand side is 1 all over f. The inverse of the right hand side is square root of friction factor all over 2. Now, if we multiply both sides by 2, we have 2 times 1 all over f equal to 2 times the square root of f all over 2. So this will cancel and this. We now have the square root of friction factor equal to 2 all over transmission factor. So squaring both sides of the equation, we now have friction factor equal to 4 all over f squared divided by f squared. So the friction factor will now be equal to 4 divided by 20.30 squared. Now let's make use of our calculator and solve out this information. We have 4 divided by 20.3 square equal to 0.001. 0.01. So 0.01. So this is a friction factor for this particular problem. Now let's resize the pipe if the flow rate is doubled. Now the question was that if the flow rate is doubled, now we say the flow rate is doubled, what pipe size is needed to keep both inlet and outlet pressure the same as that at the original flow rate. So now now let's consider this. Now we're going to use general flow equation. The general flow equation, the flow rate is equal to 38.77 F, which is the transmission factor, times the base temperature divided by the base pressure times P1 and bracket open P1 square minus P2 square divided by gas gravity divided by gas gravity divided by gas gravity divided by L Z raised to power 0.5 times D raised to power 2.5. Now we're looking for this. We're looking for that. Now the whole of this is constant. The whole of this is constant. This is also constant. Now, and what increases is just this, the double the flow rate. Now, and this is also constant. I can literally say the flow rate is proportional to t raised to power 2.5. I can now say that the flow rate is equal to the constant times d raised to power 2.5. Now, since every other thing remains constant, remain the same, the inlet and the outlet pressure remains the same, the gas flow rate is going to remain the same, the length of pipe, everything remains the same. Now, we are considering the pipe diameter. Now, when the flow rate is equal to 250 times 10 raised to power 6 standard cubic feet per day, the diameter is 19.25 inches. Now, what will it be when the flow rate is doubled, which is 500 times 10 raised to power 6 standard cubic feet per day? What is, let me see, the next internal diameter? What is the next pipe size that can now do this, where the flow, the gas, the pressure coming in, the upstream pressure and the downstream pressure did not change? What size of pipe would do that? That is the question. So now, making use of this expression here, we can now come up with, we can now say the flow rate 1 divided by the flow rate 2 is equal to d1 raised to power 2.5 divided by d2 raised to power 2.5. This is the same thing as saying d1 all over d2 all raised to power 2.5. Now, we are looking for d2. Now, we have the flow rate 1 divided by flow rate 2 equal to d1 all over d2 all raised to power 2.5. This can also be written in another form to say q1 and q2 all over q1 is the same thing as d2 all over d1 all raised to power 2.5. Now, if we multiply the powers of this expression, if we multiply the powers of this expression by 1 all over 2.5, we multiply the powers of this expression here now, this particular one, with 1 all over 2.5. Now we have q2 divided by q1 raised to power 1 all over 2.5 will now be equal to d2 all over d1 raised to power 2.5 all raised to power 1 over 2.5. So now this, if we cancel out this, we now have d2 all over d1 equal to q2 all over q1 all raised to power 1 all over 2.5. Now we have our d2, which is what we're looking for, equal to d1 times q2 divided by q1 all raised to power 1 all over 2.5. Now we know that Q2 is equal to Q1 is equal to 2 times Q1. Now if we apply this here, we have D1, we will now have D2 equal to D1 times 2 raised to power 1 all over 2.5. So D2 will now be 2 raised to power 1 all over 2.5 times D1. So what will this give us? Let's look at the calculator and solve and form it and solve it and calculate it. So now 2 raised to power 2 raised to power bracket open 1 divided by 2.5 equals to this times 19.25. So this will give us what? 25.4. So we have 25.4 as our internal diameter. So the internal diameter that we can give us that is 25.40. Now let's look at pipe data. Let's look for pipe data information. Let's open this. So let's make use of this information here. We have pipe nominal size to be 20. This to be 20. So okay, in inches we have this is inches. So the first pipe was at 20 and it was at 20 inches. 20 inches. Let's look at the wall thickness. This wall thickness is in millimeter. This is in millimeter. Let me see. Millimeter. So this is in outer diameter. Okay. Actually, they give the wall thickness in, these are in millimeters. So we needed to convert to Now they said what we got was 25, 25.4. So we had 25.4. Let's go back to this. So we had 25.4. This is 26. So 26. Let's look at this. This is 26. This is 12.7. 12.7 in millimeter. Let's check that one. So we're looking at pipe MPS of 26, and we are looking at the wall thickness of is it, let me check again. We are looking at the wall thickness. Sorry, we're looking at the wall thickness of what? Let me see. Of 12.7. Let's 12.7. This is in millimeter. 12.7. So we need to convert this 12.7 to inches. So we use it here. So invariably the outer diameter, if we're using that, we have 26 minus 2 times. Now this is 22.7 in millimeter. This times. Now we know that 25. We know that 1 inches. Sorry, 1 inches is equivalent to 20. Is it 20? Yeah, it's equivalent to 25.4 millimeter. So this millimeter will cancel out. You now have 12.7 divided by 25.4. Now let's make use of our calculator to work it out to see if this is the right pipe to choose. So we have 26 minus 2 times 12.7 divided by 25.4. So we have 25 at the dot. So 25 at the dot. So this, for me, I will use this. So let's go back to, let me go back to that chart again. Let me 26. Let me use 7.92. Let's use this 7.92. So let's say D equals 26 minus 2 times 7.92 divided by 25.4. So let's see what this will give us. Making use of our calculator, you will have 26 minus 2 times what? 7. Where is it? 7.92 divided by 25.4. So we have 25 points, roughly 25.4. So we have roughly 25.40. Okay, it's not 25.40. Will I call it 25.40? Let me see. I will call it 25.38. Let me see, 25.38 inches for the outer diameter. So now, which is roughly this value. So So the pipe we're going to make use of now, let's now write out the specification of the pipe. Sorry. So the specification of the pipe is MP26, um, MP26 schedule what? Schedule 10. So, so what we're going to use here now, B2 is now, sorry, the pipe we're going to use is MPX26 schedule 10, which is in inches is 7.92 divided by 25.4. In inches, what we get is what? Let's look at it now. 7.92 divided by 25.4. So we have 0.312, 0.312 inches. That's the wall thickness. So the wall thickness of this pipe. Now we're choosing 26 MPS of 26 inches and wall thickness of 0.312 inches. So this is the final answer. Thank you for watching to the end. Have a nice day. Also do well to subscribe to my channel and hit the notification bell so that each time I make a new video you'll be the first to watch it. Thank you and God bless. Thank you and God bless.